Now we'll study independent t-tests. This is when we have two groups that are different. For instance, males and females. And we're looking for some sort of statistical significance between those two groups. An example. A researcher wishes to test the claim that, on average, more juveniles than adults, there's your two different groups, are classified as missing persons. Records for the last 5 years are shown. At alpha, remember that's the percent or probability that we're willing to be wrong. At alpha as 0.1, so you're willing to be wrong 10% of the time, is there enough evidence to support the claim? So as before, we'll set up a hypothesis test. Here is my data in Excel. I'm going to claim that my juveniles will be represented by the first mean, or average. We'll call them mu1. The adults will be the second mean, mu2. More juveniles than adults. So my hypothesis would be that mu1 is greater than mu2. But sometimes that gets a little confusing with using Excel, so I'm going to reword it. If juveniles are more than adults, then that would mean that, so my hypothesis, juveniles are more than adults. My null hypothesis, which means there's not going to be enough to change anything, it would just be what's called noise or a lack of statistical significance, would be represented by this statement. mu1 juveniles are either less than, the mathematical opposite, or equal to, since HO always says nothing has changed, it's equals to what it always has been, mu2. Because my data, again, says more, I will be referring to a one-tailed test, also denoted by H1 is greater than. My alpha value was 0.1. So alpha equals 0.1, one-tailed test. So now I go to the Excel document. And just so you know what you're missing by going to Excel, this is the formula for calculating the z-score of these independent t-tests. I'd much rather use the technology. For those of you who are techno-reluctant, feel free to compute by hand, but be very careful and follow the examples as they're shown in your book. For those of us who want to try using some technology, we're going to have our data, and we're going to go to the Data tab. Data Analysis, and I'm looking for, at the bottom, a t-test because I have a very small sample here, and we're going to go to samples, independent, and we're going to assume equal variances. The differences between these two are more than we can go into during this class session. My variable 1 range, drag on the data, variable 2 range, drag on the data. Be careful here with alpha. In this case it's 0.1. And I'm going to go ahead and put it on a new worksheet. And here is my information. If I were using the formula, this hypothesized mean right here would be important. We didn't use it that way. We're going to look at the critical and calculated values. But we have to be cognizant of it being a one-tailed or two-tailed test. I'm going to use the one-tailed value because of the greater than symbol. I'm also going to draw that 1.39 standard deviations, and we're going greater than, so above the mean. So here's the mean, 1 standard deviation, 2 standard deviations, I'm about in here. That's my critical value. What's the calculated value? Again, you can go to the formula and figure that through, or you can say to yourself, Self, what would happen if I just looked at the printout? The t-statistic, the calculated value, is already there. 16.25. That's pretty far away. I'm going to need some more line. That means 16 standard deviations from the mean. Well, there are 2. 16 is somewhere out in here. That is my calculated value. When we're looking for statistical significance, if our calculated value is more extreme, further from the mean than our critical value, then we have significance, which means that something has changed. We are going to reject the null hypothesis. We think that mu1 is in fact greater than mu2. So our interpretation goes back to the original problem, that juveniles are classified as missing more, greater than adults. Now we need to put it in words. Something like, juveniles are classified as missing statistically significantly more often than the adults. There is statistical evidence that shows you it's not just a fluke. So now let's step away from criminal justice and head into maybe some business. We're going to look at the differences between fruits and vegetables for moisture content, 2 specific groups. Just like your old high school algebra teacher, let mu1 refer to fruits. Let mu2 refer to vegetables. This wording says differ. I don't know which one's higher or lower. So when I set this up for my hypothesis test, comparing mu1 and mu2, I don't know greater than, less than. I just think they are not equal. So H1, my hypothesis, is mu1 equal to mu2? Not what I think, which means if nothing has changed, then mu1 equals mu2 for the null. Is it one-tailed or two-tailed? Well, when we have the word differ, that must be two-tailed. What is alpha? Case, the 0.05 level of significance. So now let's go to Excel for our data. Here's our data. I need to sort it a little bit so that I have 2 specific columns, one for each potentially independent variable. I'm looking to see, are they clearly different, and is there significance between them? So I go data, data analysis. Scroll down to t-test. Again, it's a small sample. We're going to assume equal variances. Variable 1 range, that's my fruit. Variable 2 range, that is the vegetable, and it's okay to have different numbers of data pieces when you're doing independent. Alpha was 0.05, so we're safe. Failed value, since I have not equal. And I'm going to compare that to the calculated value. From Excel, my critical value, the important part that distinguishes statistical significance from non-statistical significance, is 2.13. The calculated value from Excel, in blue, is negative 3.32. Reading this carefully, I had to use a two-tailed critical value because I had a two-tailed hypothesis, not equal. Drawing this up, my mean sits right here in the middle. My critical value is 1, 2, and just a little bit beyond that for my critical value. Anything more extreme in the positive direction, and because it is two-tailed, so I also have to go the opposite. -1, negative 2, negative 2.13. Anything more extreme than either of those critical values will imply significance. Where is my calculated value? Well, it's on the negative end at negative 3.32. So it's pretty far over here. That's my calculated value. That is in the rejection region. If it's in the rejection region, I am going to reject the null. I do not think the null is true. I think my alternative hypothesis, H1, is true. So to interpret that, go back to the original problem. It wants to know an average moisture content. Are they different? So in my interpretation, I can't say which one's higher, but I can say that I have enough evidence to show that the moisture content of fruits and vegetables, I can't say which one is different, but I have enough evidence to show that the moisture content of fruits and vegetables is statistically significantly different. And now for another example of independent tests. I'm looking at the Eastern and Western conferences of the National Hockey League. My significance level is 0.05, and I want to know, is there a difference? All important pieces of information. If I let the Eastern Conference represent mu1, and I let the Western Conference represent mu2, the word difference implies not equal. I don't know which one's higher. I don't have a hypothesis, but I want to know, are they different, and is it statistically significant? Being wrong about 5% of the time, that means we're right 95% of the time. Let's set up our hypothesis test. We think that mu1 is not the same as mu2, which means our null hypothesis, mu1, is equal to mu2. We have a 0.05. My mean is right down the middle, and since I have a 2, my mean goes right down the middle, and since I have a two-tailed test, my critical value remains positive and negative. 1, 2, and a little bit beyond for my critical value. Anything more extreme would be rejected. 1, 2 below the mean, 2.10, so just a little bit beyond that. Anything more extreme will be rejected for my critical values. I compare that to the calculated value, known as my t-statistic, 1.20. This number was 1.20, which falls in here. My calculated value is 1.20, and it's positive. It is not in the rejection region. I am not going to reject. I'm going to fail to reject, meaning I might have statistical significance, but I certainly do not have enough evidence to show it just yet. So I'm going to reflect that in my interpretation, which goes back to the original problem of Eastern and Western Conference highest scorers. So my interpretation, something like this. So here's the shorthand version. If p is less than alpha, you have statistical significance. Pictorially, using our data from the last example, here's the mean. We have 1, 2, a little bit more than that for our critical value. Rejection region, 1, 2 for our critical value, a little bit more than that for our rejection region. That's the 5%. When we go to our actual data printout, we found our t-statistic was 1.20. The p-value that goes with that is 0.245. So how does that fall in the picture? 1.2 we found to be right here. 1.2 over here up in this. That leaves us with a calculated value of 1.20 and 0.24% of the curve. Notice 0.24 is much bigger than 0.05 of alpha. It doesn't wind up in the rejection region. So taking us back to our rule, 0.24. If it would be less than 0.05, we would have significance. But you can see it's not in the rejection region. 0.24 is bigger than 0.05. It doesn't fall within this portion of the curve. Therefore, we don't have statistical significance. So finishing up our problem in this shorthand method, our hypotheses are the same. We still have a difference is our hypothesis. Alpha is still 0.05, and I circle the two tail because of this difference, this not equal, and it tells me which p-value to read on my printout. It tells me to read two tail 0.245. The rule again, if p is less than alpha, you have significance. However, in this scenario, we found that p was 0.245 and alpha was given a 0.05. We don't have less than, we have greater than. Therefore, we do not have significance. We do not have enough to say that mu1 is different than mu2. We do not have enough to reject the null, at least not yet. We fail to reject the null, and our interpretation is there's no difference. It's just chance. The out-of-state tuitions in dollars for random samples of both public and private four-year colleges in Ohio are listed. Is there enough evidence at the 10% significant level to show a difference in the means? We're looking again for the word difference. We don't have a hypothesis as to which is higher, public versus private. We just think that they're different. We think that mu1 does not equal mu2, which means if nothing had changed, or if this is simply chance, mu1 would equal mu2. Private and public would be equal if it's just chance. Alpha, we're willing to be wrong 10% of the time. It's two-tailed, so I'm really looking at that alpha is going to divide up into two sides for the greater than or the less than. In my data, private versus public, two groups, data, data analysis. T-test, small sample, two samples assuming equal variances. There's the private, that's mu1. Here's the publics, there's mu2. Be careful here with alpha. I'm willing to be wrong 10% of the time. And my data shows this. For what do I look at? I'm comparing alpha 0.10 divided by 2 for 2 equal halves, 0.05. I'm comparing that to the p-value for my two tails. There it is, 0.005. So I'm going to compare that to 0.005. Is p-value less than alpha? Is 0.005 less than 0.05? In other words, would this be in the rejection region? Yes, it would. We will reject our null. We think that we have a statistically significant difference between public and private universities. So recapping, we compare our alpha value to our p-value. If it's two-tailed, you've got to cut the alpha into its two different halves, 5% on each side. If p is less than alpha, you have a significant difference between your two independent groups. I'm reading a two-tail, so when I go to my printout, my two-tail shows a value of 0.005. Remember again, the rule says if p is less than alpha, you have significance. The p-value was 0.005. Is that less than alpha, which was 0.10? Yes, that is a true thing to say. That means that we can reject our null hypothesis. Something is definitely changing. Something has made these two means different. Going back to our data, from our original data, mu1 would have been private, mu2 would have been public. Looking at their means, we can see that mu1, 16,147, compared to mu2, 9,039, which leads me to believe that private school tuition, mu1, is statistically significantly higher than public tuition. So even though I did not hypothesize which was higher, I can tell. So I can take that interpretation just a little bit further by doing just a little bit more analysis. So in short, when we're doing independent t-tests, we have two methods. The critical value method, compare the critical value to the t-statistic. Or the p-value method, compare the p-value that's given to alpha. However, you must be careful of the number of tails when you're reading the printout. Furthermore, if you're using a different statistical program than Excel, sometimes you have to divide the p-value by 2. But for our purposes, just be careful of which numbers you read.